turns into a very spread out lump of actual contraction dates. For February 5th, which had slightly fewer people, we'd produce yet another normal distribution curve that's slightly smaller and further to the right, and these people get spread out there. And what we're going to do is apply this bar to normal distribution curve operation for every single orange bar. And then we're not going to overlap them, we're going to stack them on top of each other to get total accumulative counts of how many people actually contracted the virus for each day. And the hope is that with just the orange curve, doing all of this crazy dividing, multiplying, and adding gives us a final sum that's very close to what you see in the data. So let's see how well it matches up. All that work finally gives us an image of this. So the orange line, again, as I said before, closely reflects what the news reports. And the blue line, which is trying to estimate when people actually contracted the virus, precedes it by an average of 10 days. But due to the spreading of the normal curves, it is wider and not as tall. So this kind of feels like a shift and smear in a way. I think in his coronavirus video, Minute Physics also mentioned how the graph of the true infection rates would be a shift and a spread of the reported coronavirus cases, so I'm not the only one who had this idea. But look, the blue curve here is the estimate, and up here at 50% transparency, I have the true data from Thomas Pueyo's graph. And let's overlay the two and see how good it looks. It looks like that. Not a perfect match, of course, but no estimation ever is. I'm not sure why the orange line doesn't match up with the bars perfectly because it is the actual news, but whatever. The blue estimation line though, sometimes it seems like it jumps the gun and is a couple days ahead of the actual data, like it is in the lower part of this rise, and sometimes it seems like it's behind by a couple days in the later half of the rise, and then the descent looks pretty spot on. So I think this is as close as we're going to get. I did do a bit of tweaking, so having the mean be 11 days was an option, but it didn't match as closely with the data, so I changed it to 10. Long story short, using this super presumptive guess of how long delays take, it seems like we could get a pretty good picture of where the blue estimation line is, just given the orange news reported line. With China, that's not really necessary because we have the true blue line, but with cases like Italy where we don't have the data, this estimation is all we have to go off of. So this orange line is what you've seen in the news, and you may recall that Italy went on full lockdown on March 9th. And it does seem like, oh wow, the cases continue to rise for another week and a half. Like astronomically so. So did the lockdown really fail? Well, if you look at the blue line, which is the number of actual cases, March 9th sits about right there. And you can see that that's when the curve started to bend downward and go downward. Another thing to note is that because the blue curve lags the orange one by about 10 days, we have to stop the estimation about 10 days before the present. And I'm actually stopping at 16 days before the present. So the people who got infected on April 5th, the last stragglers of April 5th infecteders are finally testing positive. I mean, the earliest ones were probably in like April 9th, 10th, and 11th, but the stragglers, we need to capture everyone, so the stragglers are finally jumping on board. I did the same for South Korea, who saw a huge spike in reported cases in late February, but then saw one of the fastest declines. And then I also did it for my home country of the United States, which has seen the largest number of cases, and the news is acting all doom and gloom about it. But you should notice that the exponential growth that we saw in March hasn't really happened in April. It's held about constant. Is that a good thing or a bad thing? Well, it's more complicated. So to answer that, we'll have to talk about growth rates. Okay, back to Hubei, China. According to our blue estimation line, for the number of new infected people per day, on January 19th, an estimated 1,430 new people got infected. On January 20th, an estimated 1,650 people got infected, and so on and so on. So every day, more people are getting infected than the day before. So as a very rudimentary definition of growth rate, I'm just going to say it's the number of cases today divided by the number of cases yesterday. So what does this mean? Well, if we went from 1,400 on this day to 1,600 on the next day, and then almost 1,900 the next day, it seems like each new day we're adding about 1/7 of the pre-existing count onto itself. So the growth rate as I define it here is going to be about 1 plus 1/7, or about 1.14. Now, if you can hold exactly constant, as happens near the very top of the graph where the count is about 3,900 for 3 days in a row, then your growth rate is going to be exactly 1. And if you're on the descent, then your growth rate is going to be less than 1. It'll be 0.9 if you're losing 10% of your new case count every day. So doing this calculation is super easy, and it gives us this green graph. So this green graph is the growth rate. It's like a relative rate of change of the blue graph. So when I was talking about that rise from 1400 to 1600 to 1800 around January 20th earlier, that corresponds to right here where the graph says that on January 20th we were rising by about 15% each day, pretty close to the 1 plus 1/7 I was talking about earlier. Now the reason why growth rate is so important is because if it were to continue the same way, it can determine the difference between a pandemic spiraling out of control and fizzling out without a huge impact. So I'm sure you've heard this all many times, but exponential growth is really sensitive to the growth rate, and it can happen really fast. So of course we want to make this graph go down, and you might think, oh, look at this, we dropped from 1.45 down to 1.14. That drop is really good and we're on the right track. But are we? Because imagine if this green line, instead of descending below 1 as it does here, imagine if it were to stay constant at about 1.14 for the rest of eternity. That would mean after every day there are 14% more cases than the day before, and I'm sure you can already see where this is going. After a month we'll have 50 times more cases per day. After 2 months we'll have 2,000 times more cases per day. And after a year, I mean, it's just ridiculous, like trillions and trillions more cases per day. Of course, exponential growth does not continue forever, but the general idea here is that if we don't get this green line to go below 1, we're in a lot of trouble. Now, if the green line hits 1 and stays at 1, I mean, that's actually not great either, because all that means is that we have the same number of infected people every single day. So if at this exact point Hubei is reporting 3,000 new infected people per day, which I think it was at its peak, then descending to 1 and holding it there will mean that 3,000 new people will be infected every day for the rest of eternity. And that corresponds to over 1 million people in a year, and so on, which is not great. So with that